So there's this, I'm going to jump around here. There's a picture over on the right, and you can maybe see Pangea right here. Have you ever heard of Pangea before? Most of you have probably heard of it. Science teachers like to talk about Pangea. And so what was Pangea? I think the picture is kind of obvious. Maybe you can't read it though, so let me zoom in and get myself out of the way. So this is Pangea, Permian, 250 million years ago. Triassic, 200 million years ago. And now they've changed it. There's no more Pangea. There's Laurasia and Gondwanaland. And then Jurassic, which you probably heard of. That's when all the big reptilian dinosaurs, maybe that's redundant, all the dinosaurs are roaming the earth. So 145 million years ago, then the Cretaceous, 65 million years ago. This is about when the big asteroid hit, we think, that they killed off a lot of the dinosaurs. And then this is today. So Pangea is just the name for the one big continent back when all the continents were together. And they're moving back and forth constantly. If I go down to North America here and Africa and Asia and Europe, they've all done this multiple times. The Atlantic Ocean, if you go to the beach, if you go to, I don't know, Massachusetts or Maine or New Jersey or wherever, that ocean has opened up like it is today, and then closed again, and then opened and closed again, and opened and closed again multiple times. So today it happens to be open. And over the last, 65 million years, it's been pretty far open. So I think a lot of people take this for granted. I take it for granted that the continents are moving around, that we have plate tectonics. But did anybody in here have any idea when people started to believe that? If you had said, the continents are moving, that's what's causing earthquakes, volcanoes and things like that, how long ago would people have said, huh? I don't believe any of that. That's nonsense. Like when, or the flip side is, when did people actually start putting it in science textbooks? And the answer is sometime around the 1950s. So it hasn't been very long. To you, maybe that seems like forever ago, but I was born in 1972. So when my mom was about 10 years old, this wasn't a thing. Nobody really knew. But let me click on this. I think this link goes to probably Wikipedia. And it's got a bunch of stuff on plate tectonics. But right in here, this is I'm citing Wikipedia as my evidence. That's kind of bad, isn't it? The geoscientific community accepted plate tectonic theory after seafloor spreading was validated in the late 1950s and 1960s. So seafloor spreading, if I click on this, it's just, maybe I should do that. And now I've zoomed way too much. Seafloor spreading is what they're showing happening really colorfully. Having trouble moving. Right here. So these two arrows. These colors make it so hard to see everything. So this is North America, and then over there is Europe, and this would be the mid-ocean ridge right there. And there's some pieces of evidence they've used to show that the ocean floor has been spreading. They can measure the age of these rocks, and then measure the age of these rocks, and then measure the age of these rocks, and these match up, and these match up, and these match up, which suggests they're born here and then they get moved away. But that's really not the point today. I do want to show you, I think this is a quick video here. It's 2 or 3 minutes on how we know that the plates are moving apart. I'm going to try to show this. I don't know if it's going to work. Last time I tried to show a video, it didn't work very well. Maybe really laggy because I'm streaming.
Christmas is coming soon, and you
gotta watch an ad first.
This is your
Looking at a map of the world, it appears
too bad.
that the eastern edge of South America and the western edge of Africa could fit together like interlocking puzzle pieces. Scientists have long noticed the similarity between the two coastlines. But it was not until the 20th century that evidence could support the theory that the continents were once connected. In 1912, a German meteorologist named Alfred Wegener introduced the first detailed and comprehensive theory.
Oh boy.
He argued that the continents had once formed.
My connection to the projector just went out. All right. So that's a good place to pause anyway. That guy named Alfred Wegener, he came up with the theory that the plates move around, but he didn't really have the theory of plate tectonics. He might have coined the term plate tectonics, but he didn't know exactly how everything happened. Or maybe he did, maybe he wasn't. I'll just let it play.
The singular supercontinent that he called Pangaea, which means all lands. Over millions of years, Pangaea broke into several fragments, which began moving away from each other, slowly drifting to their current positions on Earth's surface. Wegener supported his theory by demonstrating the biological and geological similarities between continents. South America and Africa contain fossils of animals found only on these two continents, with corresponding geographic ranges.
So it's kind of like having puzzle pieces that match up not only because of their shape, but because of their color as well. And the puzzle pieces don't match up perfectly. These shapes don't perfectly fit into those. So it's good to have this other evidence.
One of these animals, an ancient freshwater reptile named Mesosaurus, could not have crossed the Atlantic Ocean. Instead, Wegener proposed that the animal lived within the rivers and lakes of a singular landmass, which later broke apart. Other fossil evidence also supports the theory of continental drift. The earliest marine fossils found along the eastern coast of South America and the western coast of Africa date from about 150 to 200 million years ago, suggesting that the Atlantic Ocean did not exist prior to that time. Ancient rocks on the Brazilian coast also match those found in West Africa. But how did such large landmasses move? The theory of plate tectonics argues that Earth's outer layer, the crust, is composed of large plate-like sections of solid rock. These crustal plates essentially float on weaker layers of partially melted rock in the mantle below. Scientists believe that convection circulation within the mantle helps continents to move. As heat from Earth's innermost layer.
Can anybody guess what bothers me about that picture there? Let me see if I can, oh yeah, right here. If I were to draw this, I would not draw it like that. There are a few things I do differently. Any guesses? No? All right, I'm okay with this part because here we've got this rising current going up and it looks like this is going to make these two plates move apart. This would be ocean divergent. But right over here, this looks like it's sinking, which should be making these two plates come together. I don't know what they're doing. That looks just like this to me. So I think that's kind of odd. And this over here is going down without really, there's really nothing going on up above it. So if I were to draw this, I'd get rid of that one and just show this coming up and these going over. All these, I think when these videos get made, you've got, in this case, I think it was from Encyclopedia Britannica. So there's some scientists who come up with the theory that is the basis for all this. And then they hire artists to do this, and then they hire computer people to work on it. And in the middle of all that, some of these things like this crazy perfect circle, that just gets in there. That's probably just because it was easier for somebody to animate it that way.
As heat from Earth's innermost layer, the core, transfers to the bottom layer of mantle rock, the rock warms, softens, and rises upward. This pushes cooler rock downward. The cycle repeats, creating convection currents. This churning motion in the mantle appears to be a major factor in plate movement. The plates, and thus the continents, are still moving today at an average rate of less than 5 inches per year.
All right, so that's nothing that we're going to have on a test. So how we know that all this happens is not really, I want you to know why it happens and understand the physical concepts behind plate tectonics, but you don't have to explain anything about Pangea. I guess that's it. So we've got 2 quizzes. One is the quiz that we're supposed to have today, and then one was the quiz that I guess I didn't warn everybody about enough, and that's the Mafic and Felsic one. So I think what we should do is I'll give you this first. Well, which one do you want to take first? You want to do the short little Mafic and Felsic one? Okay. Now before we do it, let me just, hey Jace, let me do a little bit of quizzing of you. There are nobody's here. Let's see. But just in case somebody watching, maybe they're going to watch it later. Just in case they are. I'll make a little video of this for people who are watching. Although they actually did well on this quiz, and I think it was because we did have a little bit of time to review for it, and it was last week before they had time to forget about it. So these are the different characteristics. There's sort of the color. It's not really color, it's more shade, like light or dark. What do you call that? Yeah, I'll still call it color. Color, shade. And then there's density. And then there's the viscosity. And color, shade, viscosity, steepness of the volcano that it makes. There's where it's found. And I think that might be it, because there are 3 different places where it's, no, there's one more thing. Does anybody know what I'm leaving out on here? Ah, there's explosiveness. And if I were to pick the most important one on here, can you guess which one it would be? Like the one that, if you can remember this one, then you can remember several other ones. Because it's the one that's responsible for some of the other ones. We're out of good pens around here. No ideas? All right, well, it's viscosity. So if I put, this is kind of a weird way to organize this. This is the Mafic stuff over here. And this is the Felsic stuff over here. And I organize it according to color and shade, density, viscosity, steepness, where it's found, explosiveness. So that's the most important one. This is the second most important one. Oh, sorry, 1, 2. All right. So this Mafic, is it runnier or is it gooier when you melt it? Viscosity is how thick it is when it's molten. So Mafic, Jace, what's that? Runnier. So this one is runnier. It's like it's watery, and this one is gooier. To the point that you don't actually see felsic lava. It just might get pushed up like mashed potatoes getting forced out, but then when it gets to the top, it just explodes. So based on that, we can do this. Which kind of a volcano is going to be steeper? One with runny lava or one with gooey lava? Which one will make a big pile? The gooey one. So felsic is steeper. So if you can just remember that felsic is the gooey one, felsic is the one that's like glass. It's like similar to glass. It has a lot of feldspar and silica in it, and glass is made from basically sand that gets heated up, light colored sand, and it's really sticky. And it's when people blow glass, you can blow it because it's sticky like gum. So that's steeper. This runny stuff, this is going to be less steep. The runny stuff won't pile up. So the volcanoes it makes are less steep. And that also tells us the explosiveness. Which one of these is going to create a more explosive volcano? A volcano that's full of runny stuff, or a volcano filled with gooey stuff? Which one's going to explode? What, Harriet? The felsic, yeah. So this is more explosive because the gooey stuff plugs it up and builds up pressure, and that explodes it. But the runny stuff can't plug anything up. So these will be gentler eruptions or less explosive. Now the next most important one is density. And to me, the words dark and dense, they kind of go together. So if we knew which one is the dark one, we would know which one is the dense one. Dark and dense. Pair those together in your mind. And does anybody know which one is the dark one? Harriet? Matrix. So this is the dark one. And this may not help for you, but this one has magnesium in it, which actually isn't very dark, but it actually has a lot of iron. The symbol for iron is Fe, which is where the second part of the word comes from. And iron, if you've seen anything that's cast iron, like a cast iron stove, a lot of wood stoves or fireplaces are made of cast iron. They're really dark. So mafic is dark, and dark and dense go together. So this is the more dense kind. And felsic is light, and therefore it's the less dense kind. And that tells us where they're found. So where are you going to find dense things? So you're going to find them up high or down low? Down low. So some places that are down low are, you can find this in the mantle. You can find this in ocean crust. You can find this up higher, so you can find it in the continental crust. And you can find it on top of the seafloor sediment. I'm kind of feeling like maybe I left one of those out on the quiz. Let me see. Mantle, ocean crust. I did leave one out. I'm going to add a little bit more to this quiz. So, the people at home, you've got your quiz to take. Hopefully you will take it. I was thinking you would take it while you were here in class, but did I join a physics class, I wonder? Maybe I'm in physics. Let me see. That would be awful. But not totally unusual. I've done that before. Here, just so you can all see what I'm doing. I feel like you all have to sit there. So here's my ESS Google Classroom link. Hopefully when I click on the Meet link, it'll say Jonathan Stapleton's already there. Yeah, okay, I'm in the right spot. So we're all good. There you are. So if I join now. You ever join links or join meets you're already in? So. So you can all see this is what I'm presenting to nobody. And these are all people. I'm gonna wrap this video.